Hello and welcome to all of you. Thank you for joining this InfoShare. It is an InfoShare organized by GÉANT project, Work Package 6, Task 1. I am Susanne Naegele-Jackson, and I'm the host for this afternoon during this InfoShare. I'm very excited that we have been able to organize it around the topic of PTP. It seems to be a very interesting topic to many NRENs and our community. And I'm very excited that we have 4 experts from our community that will talk about their experiences, their deployment efforts, their testing, the issues they are running into, and also their planning, their future planning, and how they see this issue to be continued within their NRENs. They're actually from 4 different NRENs, and I think it's going to be a really great afternoon. We will have the presentations, and at the end of each presentation, you will be able to ask questions. We also have a time for questions. If we run out of time, we can always ask questions at the end of all of the presentations. And feel free to ask questions also in the chat. So let's not waste any more time. Let's start with our first speaker, Josef Vojtech. He's from CESNET, and he will talk about planning a countrywide infrastructure on White Rabbit. So Josef, the floor is all yours. We can see your presentation.
Hello, Susanne.
And we can hear you.
Hello, everyone. Thank you very much. And let's directly jump into this presentation, where I would like to briefly mention what we already built up using White Rabbit, because we have in operation almost or definitely over 1,500 kilometers of White Rabbit transmission at what we are planning for the nearest future. I definitely would like to acknowledge my co-authors, which provided very interesting materials into this presentation. And in my talk, to save the time, I'm really skip out some motivation why we need precise timing, especially in present multi 100 gigabit networks. We need the telemetry and also the sub-nanosecond timing for some research facilities. Here, I would like to spend a few seconds with activity which we called CITAF. It's Czech Infrastructure for Time and Frequency, which CESNET established, and it's a kind of national platform for cooperation into this field, into the methods of the dissemination of precise time and frequency over optical networks. And actually, we have there 3 institutes of Academy of Science and 2 faculties where the faculty of natural sciences, especially the optics department of Palacký University, is joining very soon. So this is about some brief mentioning what is CITAF. You can find more on address citaf.org if you are interesting. And here I'd like to jump to the core of the presentation, which is present state of the time and frequency distribution. On the map in upper right corner, you can see our network, and sorry, have to return back. And on the main part on the left, We now operate two different technologies. In White Rabbit, you see in blue. In orange, it's our time transfer adapters, which has been developed by my colleague Vladimír Smotlacha. And the current status is that we now connected mainly the sites where are located, you see in red cesium, standard cesium clock, and in green active hydrogen masers. On which I'll show on the next map, we in typically metropolitan areas made all the transfers bidirectional to have a better stability, but majority of long haul routes are over telecommunication lambdas, which kind of degrade the possible performance of White Rabbit. So let me jump directly to the next slide, which shows our what I promise, our plans to build countrywide time and frequency infrastructure. You see it on the right map. What's in purple color, it's already the bidirectional within single fiber, and we are going to reach all university cities which are our members, and also cities hosting some research institute with a White Rabbit timing. So it's shown on map on the right with purple dots that it requires some major upgrades, as we have quite good experiences with White Rabbit, so we decide to build this infrastructure on White Rabbit and to build it over shared spectrum with commercial DWDM systems. There are possible approaches how to overcome large distances. Different teams tried to use regenerator using White Rabbit devices. Some teams use regenerators which can regenerate synchronous Ethernet over which is White Rabbit transferred. But in parallel with this, we also running coherent optical frequency infrastructure, which relies on bidirectional erbium amplifiers. So our decision, and we already verify it, is to use the extension of White Rabbit reach using bidirectional amplifiers. You can see on the right also we reserved from some, let's say, legacy from some legacy reasons band 1540 nanometers, about 8 nanometers there, and for a future also band 1572 nanometers, not to interfere with large telecom channels which are inevitable with deployment of 800G or even 1 tera lambdas. So up to now, we mainly utilize standard White Rabbit switches. They are based on the open hardware CERN project. Into these switches can run in 3 different or basic modes. Boundary clock, that's let's say some distribution position, or to be a grandmaster, which receives highly precise radio frequency signals, or free running in the case that reference is lost. And this, you can see on the second point, time to time this might be a problem. If the switch lost the reference, it safely fall down to the free running, but time to time it's not recovering to the previous mode, boundary clock or grandmaster, and I will show later how we monitor it. It's a really pity because there is no direct indication in form of LED on the panel or some utility which will report it. You can use White Rabbit Mon, but this is kind of non-iterative or iterative command which polls something and runs. Yeah, so we have to develop some script which monitor these parameters from the procs file system and or collect these informations by SNMP. It's mentioned here that these utilities we have to write to poll and monitor white rabbit switch's status. Let's say these traditional kind of switches bring also some because they have been tailored to serve in accelerator tunnel, yeah, where the typically devices are installed and run for some time, and there are no road digging and this or rerouting or this kind of work. So typically, these switches only one port can be configured as a slave, where the reference is taken from the master or upper switch. So these switches also time to time kind of freeze and have to be restart from the far. And also these switches, for example, has one power supply unit which is kind of non usual in telecom. So yeah, they do really great work, but we decided to use some proprietary design, which is shown on the next page. Typically, these switches they are able to provide multi-reference inputs, namely 2. You can see some example of a White Rabbit 6Z16 switch, where you can connect two masters and assign them priority. So if a reference with highest priority is not available, switch tries to change to the lowest priority reference. Unfortunately, this is perfect, works. Unfortunately, it switching between references can take some tens of seconds, but I think that manufacturers are working on this issue, and this is my question to you. Have you experienced or do you think about to utilize White Rabbit switches with multi-reference, even from different vendor, different from shown here? But I'm really curious, but we'll wait obviously for the end of slides. So, as I mentioned, definitely it's necessary to monitor your White Rabbit infrastructure, especially deployed on the lines with noise and with possible rerouting. We develop some scripts, also we used SNMP polling, as I mentioned, and the presentation we did in Grafana, and you can see on the right, we monitor the uptime, and also what's interesting, that upper figure, it's a type of the device. If it's what I discussed, boundary clock, it's a grandmaster. But you can see that after loss, it will fall in the free running. It's shown in red. Next, just to have everything collected, we also monitor the input levels on the receivers, as you probably are aware that these can slightly it can have a slight influence on the delay and temperature of the interfaces, and mainly the you can see it on the top status of ports, if are up, down, or some kind of flopping. You see example of flopping on the figure. I mentioned that our decision was to use bidirectional amplifiers, which also has to be monitored. Especially, we all are aware that bidirectional amplifiers are kind of slightly complicated for operation compared to traditional telecom amplifiers, as they can start to lace if there is some problem, which I show later. on the right you can see what monitoring system is sketching input outputs and a lot of other internal things, temperatures, pump currents, everything. Up to now, we have in the network about 30 of such devices, and with our planned increase, where we will reach all the major cities, we have to go to about 70 devices, and it's becoming quite of it brings quite of work on the picture in the middle. You see such bidirectional amplification node where is 6 bidirectional amplifiers, 2 old which are single, 3 new which are even dual bidirectional amplifiers. So this is the reason why we really need to have a look on all the operational parameters. The problem of lasing it's slightly discussed here, because if we simply have a device with high gain, high means let's say 20 dB, and close to the device there is some reflection from the PC connectors or from some back splicing, it can turn into very bad laser. But unfortunately, this lasing on shared fiber can have a negative influence even on the data channels. So there are, even if we set the line optimally manually, there are some changes because of polarization dependent loss, polarization dependent gain. But even there are some service works when someone will replace the patch cord which has better, it's scratched and has a higher reflectivity. So we developed algorithm and the method here it's named Lipobatu, which is able to detect lasing and avoid lasing through some heuristic tuning of bidirectional of a gain of bidirectional amplifiers. You can see some example or some visualization of how that algorithm works. It typically finds the state. You on the right you see example of two state space, only space where are just 2 bidirectional amplifiers, but obviously it works in more on lines with more amplifiers, and typically this algorithm is working how to find the best performance in some local neighborhood. We have implemented this for the lines with coherent optical frequency, and definitely working on something slightly similar over wide rabbit transfers, but as they are based on synchronous Ethernet, this is slightly complicated because typically it's a behavior of Ethernet that independence of the optical signal to noise ratio, it's working well, and when it completely fell into line off. So, and I think this was my last slide. Thank you very much for your kind attention, and yeah, I'm giving control back to Susanne, and I'm sorry, yeah, I already took 20 minutes.
Thank you very much, Josef, for this very interesting presentation. I see there is a question by Fabian.
Yes, well, not really a question, more like a response to your question about who is using White Rabbit with multiple inputs. We do. In fact, we use the open source switches with CERN software, and starting release 6, it can do multiple inputs. It can even do the best master clock algorithm on White Rabbit. So that stuff works fine now.
Oh, great. Thank you very much, Fabian. Great to know this. So a redundant power supply is doable much more easy than multi.
Yeah, I mean the the only stuff really missing is the redundant power supplies. But as far as I've heard, Vojtech is working on that. So to provide a open source compatible switch with redundant power.
Any other comments, or I see Courage?
Just this question, Josef, you said that you had some evaluation to find out which white rabbit you want to use, which type of white rabbit you want to use for your implementation. What is the result? Are is it going for the commercial one, or the mainstream scientific white rabbit? What kind of white rabbit are you using actually?
Yeah, so up to now we have that open hardware versions, both classical, but obviously moving for the low jitter devices. And yeah, for this we definitely for this major upgrade, which will comprise about 25 or this kind of number devices, we have to open the tender. Yeah, so we will tender the White Rabbit switches.
Okay, because I for a while ago I asked about the price and the cost. I remember that this commercial one was significantly more expensive, but also they had this called a service and support cost, which was also significantly high, because the commercial one was almost nothing. So it had a very cost impact.
Yeah, of course, you are right. The price difference is really significant, but yeah, I think you catch the main advantages. There is support.
Okay, thank you.
Okay, we have another question by Eoin.
Hey guys, a bit of a noob question, but I see this initiative as a way to distribute synchronization across the whole country, across the universities. And I was wondering, is that also kind of connected, kind of, or interconnected with master clocks, meaning also synchronization of time of a central master clock, and then distributing to all of the places that you reach with this infrastructure. And mainly the aspect that I'm asking for is you already have some other clocks there. Is it the idea to remove the other clocks like GPS clocks or atomic clocks and kind of go to a centralized one, or if it's not, how are you going to deal with kind of differences in the clocks, because you will be getting, after all, two places of source of truth.
Eoin, this is a really good point. Yeah, infrastructure which I show, it basically plays two roles. One which I didn't mention, sorry for that, it's to report all the cesium clock and the hydrogen maser to the NMI time laboratory. It has been shown on that original map, because this obviously the optical way, let's say, provides the better way compared to the satellite methods. And regarding the distribution, so we definitely don't have a plan, or our members don't have a plan to remove their cesium clocks or hydrogen masers. And regarding the distribution part, having connectivity directly to the NMI time laboratory, so we will distribute national approximation of UTC. And yeah, obviously there are no clocks ticking according to the national UTC approximation. So I'm not sure if I'm responding to your question, but definitely obviously there must be differences between partial clocks.
Okay, thanks.
Okay, we have another question by Adam Vujek.
Hello, I'm a Vojtech developer and I have two questions. So first one is which version of Vojtech Switch and software do you use?
Adam, sorry, please could you repeat it? You ask about version of White Rabbit.
Of the software of White
Rabbit firmware, yeah, right. So this is probably the correct question for my colleague Vladimir. Which version do we have now?
Yeah, definitely. We use the last version. It is the standard in the normal standard White Rabbit switches. It is version 6.1, and there are negligible differences compared to the previous version, but more significant differences compared to the version to 5 version family. And concerning the Z16, there is of course the latest version. I don't know the number, but we installed it recently in December, so it's the last one. And I would like some comments to previous question about placement of local cesiums. Definitely nobody intends to replace local cesiums once that is running and so on. Rather, as Josef already said, it is part of already operating initiative SITAF to compare all atomic clocks in the country, and we use for this purpose several methods, and now we will have one other method, and that will be just unified across all the country. In reality, there are in connected institutes about 6 or 7 cesium clocks and 2 active hydrogen masers.
Okay, thank you. Adam, do you still have a second question? Because you still have the hand up.
Devices within your network. I mean, like for example, as like a lowest level.
Excuse me, Adam.
Lowest level of what?
Okay, so do you use another PTP devices like switches, routers, or whatever within your White Rabbit or with your White Rabbit network as, for example, like a lowest level?
No, we don't. We have a few PTP switches, but we definitely they are just not interconnected with White Rabbit. The White Rabbit infrastructure is just White Rabbit.
Okay.
In reality, it will be a nice test to check the compatibility, but we plan to do it very soon, just to check possible compatibility between. And concerning your question, we operate several microsync PTP boxes from Meinberg, but we didn't check the compatibility with White Rabbit.
Okay, thank you.
Joseph, one last question from myself. You mentioned the utilities that have to be developed, but you also mentioned at one point that you make adjustments to the hardware. Why, why, or have some at least proprietary solution or something you mentioned, and I understood it that why is it that you do not just get the software, I mean the hardware from the vendors and deploy? Why do you see that necessity?
Susanne, if I can summarize your question, I'm not sure if I'm correctly mentioned that we modify the hardware in case of White Rabbit, probably. So it's not my intention to say no. We have to add some scripts to collect some infos, mainly that mode information in which White Rabbit is running. White Rabbit switch is running.
Oh, okay, I see. Then I misunderstood you. Thank you very much. Any other question?
Yes, I have one, if I may. Last one.
Yes,
It's
go
Maciej
ahead.
Lipiński about the problem you observe that if you lose the mode of Grandmaster or BC, you don't go back. Can you elaborate a bit more on that? Is
we
it
are trying, but it happens only time to time, and we still haven't been successful to identify when it happens.
so you don't know the trigger for that, but you know when it happens.
Oh well, yeah. We've developed utilities. We see when it happens. When, for example, if there have been signal loss for some time and the device didn't return to the previous mode and stay for free running, so we see it.
Okay, and this is both for the boundary clocks and also the grandmasters. You see the same problems, or they are somehow different? Because in your presentation you mentioned the two.
So I probably Vladimir will can confirm that in both.
I answer this question if possible. We observed this issue mainly with Grandmaster, and it was, as we already noticed, very unpleasant when we just assumed that we distribute our cesium clock, and in reality we realized that we just distribute the local oscillator of the box of the White Rabbit. So it is, I think, a very bad and unpleasant situation. Just must say, I will send you email and describe what we observed and how. It would be probably better than discuss it here on this call. And eventually, will you participate next week in that meeting in CERN?
Yes.
Yeah. Okay. So we can continue there.
Okay. Perfect.
Yeah, but I think
thank you very much for any kind of assistance. Yeah.
I think it also happened with boundary clock, didn't it?
It
happened
another
once.
specific issue we observe is that device distributing a signal to several clocks. In case of some problems, just the device was just somewhere locked or just
frozen.
Let's say frozen in providing the system, and also for unknown reason.
Okay.
That is something that we probably can repeat because this problem is relatively often.
Okay, so we can discuss next week. Thank you.
Yeah.
Okay, thank you very much. Thank you, Josef, for this interesting presentation.
Yeah, thank you everyone for listening and questions.
Yes, it was very interesting exchange. Let's now go to our second expert, Raimena Veisllari from Sikt. She will talk about the PTP experiences they have had and are facing.
Thank you, Susanne. So I'm from the Norwegian NRN. Thank you, Josef. This is going to be faster now because our base experiences with White Rabbit, so you covered most of what I was going to talk. So it's quite a general, without going too much in depth regarding the technicalities. I have tried to put in our historical experience in Sikt regarding PTP and then what we have done with White Rabbit. We are in very early phases, as you will see. So I just wanted to cover the status, and then we have two use cases. I focus more on what we have, the services, and that's also another question towards the CESNET team. To discuss offline services that actually require this high accuracy with White Rabbit. It's something that we are also investigating. It's like our ongoing work. And then I'll just wrap it up with status and what areas we're focusing in this regard. So talking about PTP, different from White Rabbit, focusing on the 1588 2008 standard version 2, the ITU-T profiles. So historically, it's been a problem because we do not support, or all the equipment in our network, so the IP network or the packet network does not support PTP, not all nodes. We are at an early, or we are modernizing also the IP network, but it is very much as a popcorn solution. So then it's impossible to deploy PTP. So it's been very investigating it together with our system vendor, but still very passive in that regard at the packet network, because of course we don't see the value of partial time sync. Let me just also put a pointer. The 8275.2, the level of accuracy, it's not enough in use cases that we are considering. And then it's the optical layer challenges. Here it's one that, of course, it's well known as the DCF issue, so the asymmetry introduced in the optical layer by the transponders. I know that Fabian is going to cover this extensively, a very interesting presentation. And then we're talking always about the investment, and part of the ongoing work, it's always to make internally, also within Sikt, and make aware higher level management on the importance of the time and frequency distribution in the network, support in the Sikt network, which goes back then to the services that require this. And then we have identified 2 use cases, the fiber sensing, optical fiber sensing, and then also the GNSS attacks or redundancy with White Rabbit, so high precision, high accuracy, time and frequency distribution. And then on the optical network, we are at modernizing the next generation research network, as we call it, 2020, starting hopefully next year to 2030. We are at the RFQ level. Something that we need to consider discussing is that we have not taken into account the time and frequency high accuracy distribution as a requirement towards the design of the optical network, towards our transport vendors. And then we are in continuous discussion also and cooperation, not only following GÉANT. You know that Norway is not part of EU, so outside of GÉANT. However, we are in close cooperation with the forum and the team here. So that is one part of the work that we are doing towards time and frequency. So the CESNET presentation was very interesting for us. And then we are also cooperating with the Norwegian Meteorology Institute then to identify more use cases and projects together. So moving then to those 2 use cases that we have with White Rabbit. First, it's wanting to do a refresh, but Josef already covered it. So what it's interesting for me personally, but also in the discussion that we had regarding the White Rabbit switches themselves, knowing that the IEEE 1588/2019 was released, including the high accuracy profile, which is basically White Rabbit. It's interesting also, is there actually commercial switches out there that do support this as a standard? Maybe we can discuss that also offline. But with White Rabbit, one interesting possible investigation area, it's the compatibility with PTP 1588/2008. That came also as a question, because we see we do not have wide country White Rabbit network. We are very limited to 3 nodes use cases, but we see that probably with new services, it would be interesting to see with the new modernization of the IP network, cooperating interoperability with the White Rabbit network so that we minimize the number of White Rabbit switches that we deploy in the network, possibly. So this is also an area for investigation. So the first use case, it's using the fiber as a sensor. So what probably all know, it's using the sensing technology to discover seismological, environmental, wildlife activities, being in submarine. That's where we submarine cables that we have focused on, but also the same apply for, can be used for terrestrial optical fiber cables. So we have tested 2 technologies. The first is the distributed acoustic sensing, where basically we are using the fiber as a microphone. So we are sending sweeping pulses into the fiber, record the phase shifts, use Rayleigh backscattering, and then identify disturbances because of acoustic activities, interpret that information, and then you can detect whales, earthquakes, ships, storms. Then the second is the state of polarization. Also here we have tested commercial devices. And this, of course, the limit with the state with the SOP devices is that you measure it. You don't have spatial resolution with a single device. You measure it through the full fiber length. So in that regard, while we have done field trials with the Norwegian University in north of Norway, in Svalbard, we are also part now of the Submerse EU project that is a part of the Horizon Infra 2022 call. GÉANT is part of that. It's 24 partners. And one of the sites for deployment, it's the north of Norway again in Svalbard. But just why is timing then, high accuracy timing required for fiber sensing? In brief, if we use the distributed acoustic sensing, you just need to timestamp the information so that it has research value, basically. When did an event happen when? So you can use NTP, it's like accuracy, it's not required if you have a single standalone device. But if you have an SOP device and you want to deploy a system that you can have spatial resolution, that we are looking as the next step within Sikt, you deploy 2 devices on both sides, and then you can go to a spatial resolution theoretically of 1 meter, depending. The commercial devices do not support that. And if you go to that resolution of 1 meter, then you need the relative offset, let's say, between the 2 devices to be in the range of 5 nanoseconds. So you go very high accuracy requirement, which cannot be supported with PTP. And of course, you can deploy GNSS on both sides, but it's if you do not, and we do not have that in the Longyearbyen site I will show, then the White Rabbit is a solution. And then another goal of the project is, of course, to verify, estimate the differences in technologies between DAS in different types of L-band, C-band, DAS, SOP, SOP OTDR, etc. So then you need actually high accuracy timestamping to do the accurate analysis of the information. So this is where we have the site. It's up here, Svalbard region in Norway. We have a fiber that Sikt owns, or 2 fiber cables between Longyearbyen and the research center, New Ålesund. And this is where we have run most of our trials. This is a bit heavy, the slide, but if you focus on the green boxes here, we are receiving a reference from an atomic maser from Norwegian Meteorology Institute. And then in their site, we have the first White Rabbit, the Grandmaster. Then we have our own site in New Ålesund. So we have a second White Rabbit. The distance area is around 5 kilometers. And this is where we are distributing towards the first SOP device, which is going then through our WDM system, alien wavelength through our WDM system. And then we have a second DAS that goes on the L-band, so it can share the same fiber as the WDM system. And then we have a third DAS, which is C-band, both from ASN, going through dark fiber, dedicated fiber. So we have used then White Rabbit for the reference signal distribution, but we also have a GPS secondary reference clock in this site. What is interesting that I was also mentioned, we're considering now, investigating now, is when we add a second SOP here on the same link, so then we can also identify where the event happened in the fiber. And for this one, we need then the distribution, the clock reference from the third White Rabbit. And here we have a fiber that is around 250 kilometers. We have not done the performance characterization. It's something we're investigating. And then it will be interesting to talk also with the CESNET team here about monitoring of the link here. Yes, I see Maciej raised the hand, or should we take it after, Susanne?
I think after. I just wanted to say that I wanted to reply to your questions from the previous slides, but I can wait until the end.
Okay. And then the second use case when we have deployed White Rabbit, it's GNSS attacks. These are tests that are run by the Norwegian Communication Authority. It started 2020 and it goes yearly. As you can see here, it's more than 60 partners from industry, from civil society bodies. And the goal here is to measure the performance of the redundancy solutions towards protecting from GNSS attacks, knowing that GNSS has weak signals, the jamming, it's off the shelf or very cheap, can buy on Amazon equipment that can disrupt the signal. And then there is, of course, more elaborate attacks with the spoofing. So what was part of Sikt, this is not published. The 2023 tests were in September, but I linked you with the 2022 report. You can see different type of tests. What we did provide in Sikt was a 3-node White Rabbit node network where we received the signal grandmaster from one of the mobile operators. And then we went first through a DWDM link, and then we went through a bidirectional for the last hop, which was between two close by sites, giving the 10 megahertz reference signal to the Norwegian Meteorology Institute. And then the GNSS attack, or it was basically the jamming. We were part of the jamming tests towards the site 2. Okay, so then to wrap it up, what we are, as I mentioned, working on, we are still very early stages. As you saw, we only have 2 use cases we have deployed with only 3 White Rabbit switches. Those are, by the way, 7 solution, the low jitter switches, 18 ports without redundancy. And we need to increase our internal knowledge, both on the technical aspect, but also to make aware the higher level management, the importance of time and frequency distribution on the Sikt network. And then continue this cooperation, both with the national partners and international partners. We see low-hanging fruits also regarding that White Rabbit with interoperability with PTP standard switches. It's the indoor mobile coverage that we see. It's a use case where we are looking at together with the universities. So it's basically the operators, mobile operators provide indoor coverage for 5G in the campus networks, and then consider that we provide the backhaul transport, then you need an accuracy in the range of 1 microsecond time alignment error for the time division duplex, which is the new spectrum, right? The 3.5 gigahertz and it's millimeter wave. And further on, if the mobile operator wants to deploy frontal, so centralize their processing to edge or data centers, then we go down to a requirement of maximum of 100 nanosecond packet delay variation. So this is also interesting on how it will look like for us and the mobile operator, how we will cooperate. And then another area that we are looking into, it's of course quantum communication, very early stage as well. We have applied, hopefully get funding from Norwegian research authority, let's say. And here it's also something to look in, midterm, but further longer term requirements of time and frequency distribution related with quantum computing, especially quantum key distribution. So this is where I wrap it up.
Thank you very much, Raimena, for these very interesting use cases. Maciej, you had a question.
Well, actually, I wanted to answer the question that was asked during the presentation.
Even better.
So there were 2 questions. One question was about the compatibility of White Rabbit devices with 1588-2008. And as Florian from Switch noted, they should be compatible. We made quite a lot of effort.
Yeah.
No, well, we have, if they are not, it should be reported, because we have made in the recent releases,
Okay.
the intention was to make them fully compliant with the default profiles of 1588. And if they are not, they should be reported, because they should.
But has it been tested?
Yes.
So that's, yeah, okay.
As we have
there is experience.
So now for the releases, we have a set of compliance tests from external company that we run always, one. And then second, we also go to the Blackfest. So it has been tested. And if you see that is still not the case, that you should report for sure. Because our intention is to make it compliant with the default profiles. Okay?
Yeah, okay.
And then, so if you see it's not, then I would be grateful for the feedback on in one channel or the other. And then for the high accuracy, you asked whether there are commercial devices that support high accuracy. Currently, I'm not aware of any. In our roadmap, in the coming release of the Switch, which will be 7.0 in coming month, roughly, we will include a beta version of high accuracy that you will be able to switch to. So, now you're running the White protocol, which is not equivalent to the high accuracy profile. And the profile has been developed, but it has not been yet deployed in the release. So now we will have it in the release, and it will be possible to switch to high accuracy profile. And there's a negotiation mechanism to negotiate between the White protocol and the high accuracy protocol, so you can combine the devices of different types. So in the coming release, we will release it as a beta version, so you can switch to it. And if we have good feedback, then eventually it will be the default profile that will be used.
Thank you, Maciej.
So this is our roadmap.
Great, thank you, Maciej.
Thank you very much. I see another question by Amanda.
Hello, just to introduce a little bit, I don't know if you heard that so CERN is launching the White collaboration. We launched it this year month. So the idea is really to help and support people using White and finding those user cases and hosting projects around it. One of the areas of focus would be quantum networking, for example. So it's also White for quantum as part of the CERN Quantum Technology Initiative. So just to say, happy to follow up on a call afterwards and learn more about your activities, tell you more about what you're doing. Yeah.
Yeah, great. Thank you, Amanda.
Okay, great. Fabian, you're next.
Yeah, just a quick comment to Maciej's response regarding the PTP compatibility, which for us works perfectly fine. So we are running currently 3 just Linux servers connected to White, talking plain PTP. Default profile works fine, and I've also tested a Cisco router ASR 9000, also default PTP profile, and it worked fine.
Okay, thank you very much. I see one more quick question from Adam.
Question: if you have plans or wishes to actually use telecom profile in your network.
Sorry, Adam, can you repeat?
Okay, sorry, it's probably something wrong with my PC, but do you have any plans or wishes to use a telecom profile with White?
No, as I said, we are really very early stages, so we have not considered if that is required in a way, or if you have a use case in a way. But it all depends on our system vendor for the IP network, right? And what they provide and what is the easiest, more feasible solution. So it's something also to test maybe.
Okay, thank you.
And Fabian, you wanted to add something? Or okay. Okay, so thank you very much. It was very exciting to hear your use cases and experiences. Let's now move to Ireland and to Eoin Kenny, who will talk about HEAnet's experiences with PTP and future plans.
Thanks, Susanne. And say this will be a lot easier for people to understand. I think we're definitely not as advanced as others in our timing experience, but I'll run through what we have. I suppose about 2 years ago we started with, we just created an informal timing group with some academic and industry partners, and just to see what we could do with timing. And I won't, I'll just move on quickly because some of these are people have talked about. But I suppose just really for ourselves, we tried to identify some use cases that we were interested in and so forth. And one was just from the people we were talking to, was just very much just with 5G test labs. We have a number of them, and could we provide frequency and phase synchronization using PTP to those labs? Also, you know, just 5G campus networks is also quite interesting, and could be, we could do something there. Electricity grid, there's PMUs, phaser measurement units, and smart grid is just another one of the use cases that one of our researchers is very interested in. And similarly, we're involved in LOFR, so I know there's some talk with White Rabbit and LOFR in the Netherlands. And we're also involved with a national timing grid here in Ireland, and that's quite interesting for monitoring different cesium clocks, basically. But also just being able to provide accuracy to our national metrology organisation here in Ireland was also very much of interest for some of our researchers to be actually able to say that they could reference back to our national metrology lab. And then we're also just talking with one of the equipment vendors, just with Microchip, about ePRTC, just by connecting the TP4100s that we have from Microchip together. And also we're just, one of the researchers was interested in using PTP for time synchronization with P4. And also our friends in JISC have talked with the Persona people about adding PTP support to Persona, which I think would be a very interesting idea. And I think work has started on that. But I suppose for ourselves, we were just thinking of what services we could actually provide. And I suppose I'm far from an expert on PTP, and I've been on this learning journey about what's possible. But very much, you know, I was surprised really with just the number of flavors of PTP is just, you know, mind-boggling and confusing, to me anyway. But you have different levels of accuracy, I suppose, and resolution here. PTP, you know, being at one, White Rabbit and PTP, another dedicated wavelengths and so forth. But yeah, it's just, I suppose, give you an idea of some of the services we are thinking of doing, but at the moment we're very much just focused on PTP on its own, so plain old PTP. This is one example. I think it surprised me when I came to this is, we have these TP4100s, which are rubidium sources, but we have one in Ireland with our national metrology lab, and that has a cesium source, and it's connected to a TP4100. So that's kind of the most accurate source that we have. But just in terms of the different profiles, it's quite interesting to see what we can get from our TP4100. And I suppose of interest to our community, or well, to me anyway, were the 825.1, but that requires Sync-E. So this is very much, and PTP. So it's full timing support really from the whole network. You need all your network to do this. And then there was partial timing support with 8275.2. And this can operate over existing networks, you know, with or without router support. So I suppose very much for myself is focusing on 82752 and trying to see what we could do over our network, because we have a Juniper router network. So what have we done? We have 3 of these TP4100s on our network that we have access to. One connected to our national metrology lab, which is UTC for Ireland, basically. And that has, we have two of them providing G8275.2 unicast, and we've one providing just multicast V4. It works fine, but I suppose the problems with the multicast V4 is just getting it to the end user will be a problem. But it does work across our core network. We haven't gone near, we haven't used transparent clocks just because we use MPLS in our core network. We've just basically configured our routers as boundary clocks. And using 82752, we've just been focusing on phase, frequency, and time distribution. And we've just been enabling it, at those universities that are part of our little research group as and when needed, so on a case-by-case basis. So we haven't enabled it everywhere. So just some of the issues we've encountered with the TP4100s. Just in case anyone else has TP4100s and has a few and is trying to implement PTP on them. A couple of ones, just the version 2.3.6 of code, NTP in the box hangs once you hit about 20,000 packets per second. Hard to believe, but it only has dual stack V4 and V6 in this day and age in a later version of 2.3.6. We had to go back to using 2.2.3, which meant we needed physical separate interfaces for our V4 and V6. So we couldn't use dual stack because of the NTP issues we were having with the boxes. The boxes do NTP and PTP for us. We've also encountered in the latest version a PTP bug that one of the guys has identified with us who's working with us, Zenek, and there is a workaround, but it's basically incorrectly implemented PTP 1588/2019 on the TP4100 in that version of code. There is a workaround if you're using Linux PTP playing with it, but it just might, if someone is doing that, it might be useful to know. And similarly, just when you are looking at your TP4100s, you're looking at with the licenses we have, a max of 16 clients. So not particularly an issue for us because we connect them basically to a Juniper pretty early on and distribute from there. But just Juniper router support is, there's a very good day one deploying guide. I'd highly recommend it. That's the place to start if you are looking at trying to do PTP on your Junipers. Juniper will tell you our routers support PTP, but that is a meaningless statement, to be very honest. It really does. There are loads of gotchas. It really depends on the hardware. It really depends on the platform. There are so many different combinations of different things. But you can get PTP working quite easily, to be honest. As I was saying, just with our MX, we have MX 480s, 960s, 104s. 8.2.75.1 is supported. Juniper will tell you supported, but hey, it doesn't work on an MPC4, so for SyncE. But we have stayed away from 8.2.751 just because of what's involved. Enabling SyncE on all your routers is quite a task. And then you're also into your transponders. Do they all support, SyncE as well? I suppose the easy man's effort, or the way to make, if you quickly want to do something, 8.2.75.2 unicast is the way forward that we found. We found it quite easy. Just a couple of other ones. Juniper refers to enterprise PTP, but that's only for the QFX and as multicast. So just in case you do come across that one. What was I going to say? So typically your Junipers, the MXs anyway, the default profile is just IEEE 2008, and you can use unicast negotiation with that and our TP4100s, and that works fine. But we've also, on our newer boxes, we've been using G8275.2 enhanced. on our Junipers. But just to give you an idea what this looks like in terms of configuration, this is one of our TP4100s. You can just see the profile we've selected. It's just there in yellow, 82752, unicast layer 3. You have the clock accuracy within 100 nanoseconds, and you have just the MAC address then of the grandmaster in this case for our case. And then similarly here, it's just a config on the Juniper, so the snippet, we have a slave and a master. So this slave is to that particular TP4100 over our Juniper network. And then this ACX, this ACX7024 is then master for a downstream client. And here, this is just on the Juniper ACX 7024. You can see just time and frequency traceable, and that's the MAC address highlighted of the grandmaster. And there you can just see that it's phase aligned with itself, basically. But I suppose for me, that's just a whirlwind tour of, PTP G.8275.2 on across our Juniper networks. It's easy to do. It does work. The only thing, I suppose, the questions I come up with once I get to this stage is how accurate is it? How do you verify the accuracy of it on your routers? These are questions. I'm sure I have a whole bunch of experts here, so hopefully some of you will be able to help me with these questions. And then we'd also, how do you guarantee it's within, X nanoseconds if you want to provide an SLA to your end users? I know 8275.1 will be more accurate than .2, but how much is it really worth it for, the use cases we're looking at? A lot of the use cases I think we're looking at, I think 82752 is probably good enough for a lot of them. A lot of the 5G test lab ones, it appears to be good enough. But I'm also just curious, if I know people here are very much focused on White Rabbit and 10 to the -9 and -12 accuracy and stuff like that. But I'm still keen. I'm keen on just PTP, over our core NREN networks. And I don't know if it's gonna. There's no real guide out there or how to do it or how to implement it. And also just monitoring PTP in your routers. How do people do it? Do people? And just also, is there some potential interest in some type of incubator proposal here in terms of how to run PTP, whether it's 8257.2 or something else across our core router networks in NRENs. So that's a little whirlwind tour for me about where we're at and where we're going, and I'll leave it there. So thanks, Susanne. Thanks, everyone.
Thank you very much, Eoin. That's really an interesting question with the comparison of G8275.1 and 2. That would be interesting really to compare and also see where, like you said, where this would leave the use cases. I see there's a question by Raimena.
Yes, it's more a comment regarding the use case that you have with 5G on campus networks that we are also looking into, and the two profiles. I know that we have had the mobile operators from experience in Norway have had a big headache because, of course, the network was not supporting PTP, and then they deployed the partial time sync, and the accuracy, it's not good enough because the time alignment error for TDD, so time division duplex, when you go on the high frequencies, needs to be 1.5 microseconds end-to-end to the air interface. And then the allocated from the mobile system vendors, it's the allocated for the transport, it's 1 microsecond time alignment error. And that is something you can never achieve with partial time sync because you can control the packet delay variation in those nodes that do not understand PTP. So that is something that has been solved with GNSS, at least in Norway, but the National Communication Authority has put the foot down in a way that operators need to support the full profile because GNSS is vulnerable to attacks. So this is at least our experience regarding this question and that use case.
Thank you very much for sharing that. That's good to know. Thank you.
We have one more question by Adam from PSNC in the chat. Implementing G8275.1 can be quite challenging in a MAN, as careful design will be necessary to avoid timing loops. It's something I'm thinking about. Perhaps someone has some experience with it. I guess this is not a direct question maybe to you, Eoin, but to generally the audience. So let's leave it at that since we're running late in time. Thank you very much again for your presentation, Eoin. And if anybody has a comment to Adam, please place it in the chat. Let's now go to our final presentation by Fabian Mauchle from Switch in Switzerland about PTP over transponder links.
All right. Okay.
We can hear you and...
See.
Okay, we can see it. Go ahead.
Okay.
Mm-hmm.
So welcome to the last presentation for today about PTP over transponder links. So maybe I'm actually going to answer some of the questions of the last presentation. So to provide you some context, when we first thought about doing something with time services, kind of the goals we wanted to have it run over our network. So we need to cover spans of more than 80 kilometers. Just kind of as an arbitrary goal at the time, we tried to aim for the primary reference time clock accuracy by G8272, which is less than 100 nanoseconds to UTC. For those who are familiar with the standard, there's also an enhanced version, which is below 30 nanoseconds. From the network point of view, we were running at 100 gigabit at the time, with already kind of envisioning future 400 gig links. Most of the links are using DWDM transponders or actually Mach-sponders, so the typical 200 gig line-side optics. Even GÉANT uses very similar technology. Kind of that's the frame we are working in, and kind of the TLDR response regarding transponders and PTP, basically you don't. The really long answer is it's not about PTP, it's about synchronous Ethernet, or generally layer 1 synchronization. So kind of a quick recap on Ethernet. Basically, if you have two Ethernet nodes, one on the left, one on the right, each has its local system clock. You get the Ethernet MAC and the PHY blocks, and Ethernet is designed in a way that your receive clock, so your receive clock is synchronized to the transmit clock of the other side, and the other way around for the return path, which means that the receive clock is actually asynchronous to the local system clock. If you add PTP to that, it's basically just a protocol on top, using hardware timestamping. But that by itself doesn't really synchronize the clock. So the kind of default mode of PTP is clock steering. The default profile uses 1 update per second. You can go up to, I think, 32 updates per second, just to kind of steer the clock in the right direction. But yeah, the accuracy is not all too great. So sadly, I couldn't get the required test equipment to really provide measurements of a router. So instead, I opted to try to simulate this with White Rabbit switches, forcing them to not talk White Rabbit, but talk plain PTP, and also not do the layer 1 synchronization and do the 1 Hz clock steering. It's in a lab environment with a very short 1 meter fiber. So basically eliminating any external influence on the clock accuracy and just focusing on kind of this software clock servo, which gave me a frequency accuracy of about 10 to the minus 8 at 1 second interval, and total time error between the two boxes of 100 nanoseconds peak to peak, with a standard deviation of 16 nanoseconds. Now, if you just think, okay, 100 nanoseconds is enough, it's almost the PRTC requirement. Don't forget that this is just the clock servo. We are not considering any influence on the fiber itself with this setup, or any asymmetries and so on. So this would definitely not meet the standards of PRTC. To do that, you usually need the layer 1 synchronization. So typically we're talking about synchronous Ethernet, which recovers the Ethernet receive clock and uses a PLL servo, usually with some kilohertz, maybe even megahertz servo bandwidth, to keep the local system clock in sync with the Ethernet receive clock. And usually you'll even keep the PTP, so running synchronous Ethernet by its own. Yes, it's possible, but usually doesn't make much sense. So you keep the PTP to get the time of day and correct for delay variations in your fiber. Again, I tried to do some measurements with White Rabbit. Now kind of running at full White Rabbit accuracy. So the frequency part, I assumed that synchronous Ethernet would achieve about the same accuracy than White Rabbit layer 1 synchronization, at least for short time spans, which is in the order of 10 to the minus 11. Quite good. Keep in mind that with plain PTP and without the asymmetry estimation that White Rabbit does on longer measurement spans, it will be worse than the PTP stuff, than the White Rabbit stuff, sorry. But just to give you some rough estimate about what we are talking about, the absolute time error, I guess, would be better than 8 nanoseconds. 8 nanoseconds is just the byte clock of a 1 gigabit Ethernet signal, which is kind of your resolution of the time of the hardware timestamp. So you should get better than that. Noise isn't really a big issue in relation to those numbers. And just to give you a perspective, the full White Rabbit accuracy is kind of a peak-to-peak of 0.1 nanoseconds, and the standard deviation of 20 picoseconds or even lower. But that's really the White Rabbit part of it. And again, we are only talking about a very short link. So the typical synchronous Ethernet with PTP will not cover any temperature fluctuations and so on. So the actual time error will be slightly greater than that, especially if you are chaining such links. Now, the actual issue is what happens if we insert a transponder. So up to now, we only had 2 boxes connected back to back. But for the long links at 100 gig, we use transponders or muxponders. And basically, each transponder has some local clock, needs to have them. They are specified to 20 ppm, which is, compared to the figures you have seen before, rather bad, but enough for OTN. And if we would just enable synchronous Ethernet, yeah, most likely we would just synchronize to the last transponder and not to our actual source clock that we want to. So maybe we have transponders that do clock recovery on their own and actually can pass the synchronous Ethernet. Maybe not. That's kind of the big issue here. And how can we solve it? Basically, the very first point, if you don't need synchronous Ethernet, so the basic PTP stuff without synchronous Ethernet is good enough. Basically, don't worry. Works fine over transponders. They don't influence the PTP on its own. It's just the synchronous stuff should be fine. However, if you need it and you're going to use transponders, basically all what we figured is all the muxponders, especially the 2x100 gig OTUC2 links, most likely will not work. Just by the fact that they are muxponders, they have 2 input signals, and how to decide which one to synchronize to the OTN side. So most likely won't provide it. The kind of one-to-one transponders, 1040, 100, or 400 gig, maybe they will work, maybe not. That's something you need to check with your vendor. Ours, which is Ribbon, told us no, they do not synchronize on layer 1. So we didn't even try. Just figured it most likely would not work. Maybe you're lucky and you actually have a DWDM system which comes with its own full-blown clock synchronization and primary reference inputs and stuff. Then yeah, use that. That's designed for it. On the other hand, what to do if your transponders don't work? Basically, the solution is go alien. So put colored optics in your router, connect them back to back for 1 gig interfaces. You can get up to 160 kilometers unamplified, 1,000 plus amplified easily. For 10 gig, it's dispersion limited. So again, if you still have dispersion compensation in your network, no big deal, should work at very long distances. The very interesting question will actually be, what about 400 gig coherent optics in your router, the ZR Plus? Haven't been able to test them yet, but that will be quite an interesting result for these applications. If that works, that would be absolutely great. With that, we can actually do, if we run them down at 100 gig, we can do 1,000 kilometer plus amplified synchronous Ethernet, no big deal. The kind of last option is to use not your routers for PTP, but use specialized devices. One option is to use kind of the vendors you usually buy your grandmasters, PTP grandmasters, Meinberg, Oscilla Quartz. I'm sure there are multiple others. Those devices usually can also run as boundary clocks. Will still be alien DWDM, PTP plus synchronous Ethernet. but maybe they kind of act better than your routers if you anyway have to do some alien transmission. Or, as we already heard multiple times, go for White Rabbit. For that, kind of, it's recommended to use bidirectional links. So most likely you will end up BDR optics in some CWDM size channel to not interfere with your DWDM system. Which for us, yeah, we went that way. We first tried the very first solution, kind of just do PTP, let's see what happens. And with our very first experiments, we actually had some issues getting two routers to sync without synchronous Ethernet, just PTP. Maybe it was some software issues. When I tried it again in preparation for this presentation, it did work just fine. So not sure why. Again, the transponders weren't really an option for us. So we started talking to oscilloquartz in that case, which could provide us something, even something that should achieve our goals of transporting the PRTC over long distances. But in the end, we decided to just, if we're anyway going to do some specialized equipment, why not try kind of the best accuracy we can get and see how far we can come with that. Yeah, so that was my brief story.
Okay, thank you very much, Fabian. I see no raised hands. Are there any questions? Oh, Maciej, please go ahead.
I just have one comment on the OTN transport. So, okay, I'm not an expert here, but one of the amendments to IEEE 1588 2019, the first one is mapping over OTN of the PTP protocol. And that would mean that in principle, we should expect some OTN devices that support PTP synchronization. What would be the performance and how this is done? I'm not sure, but we did pass this kind of amendment to PTP to map PTP over OTN networks. So I would expect that there will be something in the future.
Yeah, again, ask your vendor.
Yes, exactly.
They need to tell you what they have implemented and how good it should work according to them. Again, for us, the response was no, we have not implemented it, and we are not bit synchronous.
Okay.
I see one comment in the chat by Shankar Monda. You missed one, FiberLAN RXGs, and there's a link to it.
So that would be what a...
It does Syncy, it does bits, it does PTP, GPTP, but it's not a router, it's a switch.
Right, so then we are again at the specialized PTP equipment.
Yes, and you can do up to, we have tested in Telekom Austria, we have tested up to 800 kilometers, 80 kilometers, sorry, with an accuracy of half a nanosecond with the same configuration that you showed here for long-term testing of like over 7 weeks. And we came up with half a nanosecond, and that was in 2019. I mean, that was a long time back, and after that, we did not have any, but the switches have developed. So you can expect something more, higher distances, bit, Syncy, PTP, GPTP. I'm not an expert on the PTP profiles, that I have to say, but that's the reason I put that stuff in the link. And currently it's up to 200G, but you have to use splits of 25G.
Right, okay.
Okay, so you know, I mean, the problem is with the fiber, and it's not with the transmission. It's a problem with the quality of the fiber that's there. So, because you will have interferences there of some kind or the other if you go on long distances with a fiber. So it's more of a fiber issue, not a transmission issue.
Yeah, right. So that's on the other, it's kind of a little bit similar to White Rabbit in terms of timing accuracy, and then it's a matter of how do you combine the data traffic, keep it separate, or
No,
combine.
the data traffic, it will be forwarded together. It's
Yeah.
it's a single interface, but the data traffic would be 25G. It would be 25G. It wouldn't be more than 25G. You can aggregate it somewhere.
Yeah, exactly. And that's kind of the thing, that if 25G is okay, I mean, you can do White Rabbit with 1 gig. So if that
So
if
you
that
need to
suits you.
transmit the data, because other than the data, you do not have any sense. I mean, what we do is that we transmit the data as well together, and it's the maximum that we can get is 25G with the accuracy that we have. You can do more data together with this time and frequency, but on the layer 1 or the layer 2, but then you will have your issues with interferences. You get me? So it's one single fiber transmitting the data and the time and frequency. And the data packet should not be more than, I mean, the port is not more than 25G. Yeah. Is it clear or unclear?
Well, to me, it's clear enough.
Okay.
So again, as I said, if you want to do 200 gig and more, you kind of need to separate it and need a special solution to transmit your time.
Yeah.
Which obviously this can be a special solution.
Okay, thank you very much. Unfortunately, we're at the end of our time. I want to thank the speakers again for sharing their experiences with us. And I would also like to thank the audience for making it a very exciting exchange. And this recording will be available on our GÉANT YouTube channel and also on the GÉANT events page. And I would like to close out and let you know that we have another upcoming Work Package 6 info share on February 14th, Network Performance and Monitoring Workshop. So please join us then as well. And thank you for coming this time. Bye-bye.